Да не надо
zero
играть
to
просто
lambda,
все, да.
where lambda is the wavelength.
Ну нет, наоборот.
The trick to integrating this expression is to recall that sine squared x
Черт
equals
уже.
half times 1 minus
Пару
cos
звуков.
2x. And a simple calculation then leads to the following expression for the energy per wavelength. If we write this in terms of the frequency f, we find that the energy per wavelength is 2 pi squared f squared a squared mu. And the remarkable thing that we notice is that the energy of a wave is proportional to the frequency squared multiplied by the amplitude squared, which was exactly what we found for our simple harmonic oscillator. This shouldn't come as too much of a surprise, since a wave is nothing other than a series of coupled harmonic oscillators. Now it is worth mentioning that although we base our analysis on the specific example of a rope, this analysis generalizes to waves traveling through all sorts of media, and in all cases the same relationship between energy, frequency and amplitude holds true, as it should for all of the simple harmonic motion. So the natural question arises, if the energy of waves and harmonic oscillators obey the same relationship, is the same true when we factor in quantum mechanics? How do we describe a quantum wave? Well, it turns out that it's relatively straightforward. Since a wave is simply a series of coupled harmonic oscillators, it follows that the properties of a quantum wave are very similar to the properties of the quantum oscillator. In particular, the energy of a quantum wave can be expressed in terms of Planck's constant in the frequency as n plus half times hf, where n tells us how many quanta of oscillation we have in our wave. We see that each quantum of the wave carries energy hf. That waves obeying this equation have a minimum possible frequency. Now the key point is that when we add quantum mechanics into the mix, this minimum frequency constraint translates into a constraint on the minimum energy that a quantum of this type of wave can have. In particular, we see that the minimum energy of a single quantum is Planck's constant times the minimum frequency. And it follows that if the available energy in our system is less than the minimum quantum energy, then you cannot make a single quantum of this type of wave. And this simple fact is going to play a crucial role in our analysis of quantum fields. So what exactly is a field? In physics, a field is simply a function of space and time with an associated equation of motion that describes how the function may change with time. Now the simplest kind of field is a scalar field, which simply consists of a number assigned to each point in space. For example, if you were to measure the temperature at every point in space, then we could define a temperature field by assigning a number to every point. To help visualize this, we might use a color gradient, and we could then use an equation such as the heat equation to understand how the numbers change in the presence of a new or changing heat source. Another important type of field is known as a vector field, in which we assign both a number and direction to each point in space. For example, if you were to measure the wind speed and direction at every point in space, then you could produce a map consisting of arrows located at each point in space, with the length of the arrow being proportional to the speed, and the direction of the arrow indicating the direction of the wind at that point. Another classic example of a vector field is the electric field, which exists around electric charges. In this case, the arrows at each point show the direction and magnitude of force that would act on a positive test charge circle, then this causes the field to ripple, sending a disturbance through space. In the case of the electric field, these ripples are in fact light waves which travel at the speed of light. It was during the 19th century that James Clerk Maxwell first discovered that it was possible to combine the equations of electricity and magnetism to arrive at a wave equation which predicted the speed of electromagnetic waves should be 300 million meters per second. The remarkable thing was that this speed perfectly matched the recently measured speed of light, leading Maxwell to conclude that light is an electromagnetic wave. Now, a natural question to ask is, if light is travelling at 3 times 10 to the 8 meters per second, then relative to which frame of reference is this velocity measured? This was, in essence, the question considered by Einstein whilst working on his theory of special relativity at the beginning of the 20th century. One of the key features of Einstein's radical theory was that all observers would measure the same velocity of light, irrespective of their frame of reference, implying that different observers would measure the passage of time differently according to their relative motion. Furthermore, according to Einstein's theory, it was possible for light to travel at a constant speed through empty space without a medium to support it. According to this picture of reality, an electromagnetic wave is a self-propagating ripple of an underlying relativistic field, namely the electromagnetic field. Now, it turns out that the electromagnetic field is not the only example of a relativistic field. There are in fact 2 broad classes of relativistic fields which we are going to focus on, corresponding to the unmodified and modified wave equations that we encountered earlier. The only difference now is that we're going to label our relativistic field function using psi, and c refers to the speed of light. So what exactly are these equations describing? Well, firstly, both of these relativistic wave equations describe waves that carry information and energy from one point in space to another. Furthermore, it's important to emphasize that a relativistic field does not describe the property of some ordinary physical medium. There is no underlying medium. In fact, as far as we can tell, relativistic fields may be among the most fundamental elements of reality. And so we are almost in a position to finally understand what a fundamental particle is. All we need to do is combine our knowledge of relativistic fields with our knowledge of quantum mechanics. So let's do this. We will begin by focusing on the modified relativistic field equation. We have already seen that the frequency of the waves in such a field are constrained and there is a lowest possible frequency. If we square both sides of this constraint equation, then we find a Pythagorean relationship, which is always a good sign in physics. What we now want to do is take our Pythagorean constraint and combine it with the energy relation for a single quantum. If we multiply both sides of our frequency constraint equation by Planck's constant and make use of E equals hf, then we arrive at the following total energy relationship. Now, hopefully, if you've watched my video on Einstein's theory of special relativity, then the form of this equation should remind you of the famous energy-momentum relationship from Einstein's theory. According to Einstein, the energy E of an object or particle is related to its momentum p by the equation E squared equals p squared c squared plus m squared c to the 4, where mc squared is the rest mass energy of the particle, which exists even if the object is not moving, and therefore you can think of the rest mass energy as the minimum energy that the object can have. Now, we've also seen that waves obeying the modified relativistic field equation have a minimum frequency, and furthermore, according to quantum mechanics, this implies that a quantum of this field has a minimum energy of Planck's constant times the minimum frequency. And so it's very tempting to equate mc squared with Planck's constant times the minimum frequency. And it's also tempting to equate the first 2 terms in each of these expressions and set p squared c squared equal to hc over lambda all squared. So what are these relationships telling us? Well, if we begin by rearranging the second equation, then we recover the famous de Broglie relationship linking the particle property of momentum with the wave property of wavelength. But what about the first relationship? Well, if we rearrange for m, then we see something truly remarkable. This equation is telling us the mass of a quantum of this type of relativistic field. In other words, we see that any particle with mass can be thought of as a quantum of a relativistic field whose waves have a minimum frequency
and therefore a minimum energy. And furthermore, we see that what we refer to as mass is simply the minimum energy of a vibration of the quantum field divided by the speed of light squared, which is a truly remarkable revelation. But what about massless particles? How can we describe those? Well, we see from the mass equation that if the minimum frequency is set to 0, then the mass also becomes 0. And this fits with what we've already seen, because if you recall, there is no minimum frequency constraint in the unmodified wave equation, and furthermore, we know that light, which is massless, is described by the unmodified wave equation. So if we set the minimum frequency to 0, then we see that not only is the mass 0, but we also recover the familiar photon-energy relationship that Einstein introduced to explain the photoelectric effect. And finally, if we set the mass equal to 0 in the energy-momentum relationship, we recover the familiar expression for the momentum of a massless photon. And so now we are finally in a position to answer the question that was posed at the beginning of the video. What is a particle? Hopefully, if you followed this far, then you'll be in a position to understand that a fundamental particle is simply the smallest possible vibration, or quantum, of a relativistic quantum field. And furthermore, we have seen that particles with mass are described by the modified relativistic wave equation, whereas massless particles are described by the unmodified relativistic wave equation. And it is this view of reality that lies at the heart of the standard model of particle physics. Within this framework, the quantum fields are considered fundamental, and the familiar particles of the standard model appear as the quanta of these fields. For example, the smallest possible vibration in the electron field is called an electron. Similarly, the smallest possible vibration in the electromagnetic field is a photon. And then there are quark fields and gluon fields and a Higgs field. And so we see that every particle in the universe is a tiny quantum mechanical ripple of the underlying relativistic field. And that is where our journey ends, for now. Of course, there are still many questions left to answer. For example, what determines the minimum frequency of our modified wave equation? Why do some particles have mass, whereas others are massless? How do quantum fields interact with one another? And what is the relationship between matter and antimatter? Answers to all these questions exist within the highly successful framework of quantum field theory, and will no doubt form the basis of future videos on this topic. For now, however, I think it only appropriate to end with a quote by one of the pioneers of quantum theory, Wolfgang Pauli. The best that most of us can hope to achieve in physics is simply to misunderstand at a deeper level. Well, I hope that I've helped to deepen your misunderstanding with this video. Thanks for watching.
Perhaps one of the greatest advancements in physics occurred during the 20th century with the unification of special relativity and quantum mechanics. This incredible theory has electrodynamics to quantum dynamics and beyond. Exactly is a quantum field? To understand, start by talking about classical fields. One common example of this is an electric field. Field extending all the way to infinity. This field is closely related to how strong of a force a second charge will feel from the source. As we get farther and farther away from the source, the strength of the force that a second charge will feel will get weaker and weaker, and so the value of the electric field gets smaller and smaller. However, this fields are modeled as fields, even though they're not technically continuous, where field give, for example, the density at a certain point. It continuous object which has some value at each point in space and time. So quantum field is simply a field which obeys the rules of quantum mechanics. This concept might seem a bit strange. How can a quantum when quantum exactly means cut up into distinct pieces? Also, how did the theory of fields give us the study of particle physics? To answer this, let's start by trying to understand a classical field theory, the simplest of which being a string. So, say we set up our system in a way where the string is forced to stay in a circular loop. Now, the string in principle has some elasticity to it, so we can stretch it and compress it. We also could imagine segmenting this string into teeny tiny little pieces, where each one of these pieces will only feel a pull from the pieces right next to it. Now, if we treat each of these tiny pieces as rigid bodies, we can see that it is beginning to look like a bunch of small masses connected together by springs, also known as harmonic oscillators. Specifically, it looks like an infinite number of these harmonic oscillators, infinitesimally close together. In fact, this turns out to be a great way to mathematically describe field theories. So instead of just jumping straight into the case of the string, let's instead look at the more intuitive case of a bunch of masses connected by identical springs in a ring. Here's the setup. We'll take our ring of harmonic oscillators, displace a single one, let go, and see what happens. Let's start with just a few, then really crank up the number of oscillators to see what we might expect from a true field theory. In these simulations, the springs which are compressed will be red, and the springs which are extended will be blue. The more compressed, the more red, and the more extended, the more blue. When the springs are relaxed, they'll be gray. Okay, let's see what happens. When we start with a small number of masses, there aren't a whole lot of patterns to see. Once we release the mass, everything just starts oscillating back and forth in a messy way. However, we can immediately see something interesting. It looks like it takes some time for these oscillations to actually reach the other end of the ring. In other words, it looks like there's some maximum speed that the forces can travel through this ring. When we get above about 100 masses, I'll make a few changes due to the fact that it gets very hard to see what's going on with individual masses and springs. First, instead of drawing all the springs and masses, I'll only show the colors of the compressed or extended springs. Second, instead of starting out by displacing only a single mass, we'll start by compressing all of the springs in a certain region and extending all of the springs in the other. This makes more sense to do anyway, since our end goal is to describe the continuous string, and it doesn't really make sense to displace a single piece of a continuous object. So, for about 100 masses, nothing's really too much different from the cases with fewer masses. However, watch what happens when we increase to 500 masses. It looks like two copies of the initial compression and tension regions start to zoom around the circle in opposite directions, while everything else seems somewhat stationary. But it isn't perfect, so they start to develop tails of oscillating masses in their wakes. When we increase the number of masses even more, these tails take longer to develop and stay smaller than the case of 500 masses. By 5,000, the tails almost don't even show up at all. This pattern, of course, continues until we have a true continuum, in which case we don't develop the tails at all, and we just get these two copies of the initial state moving around the ring at a set speed. So already we see how something which looks sort of particle-like could arise from a field theory. If we start with pieces of our field in a certain state, these pieces will keep their form and move around like we might expect a particle to. However, these aren't truly particles. They're really just regions of high and low density in the string. In other words, these are sound waves which propagate around the string. But we aren't done. There's nothing quantum about this field theory. So how do we upgrade this classical string to a quantum field theory? Well, it's easy. Instead of using classical harmonic oscillators, like a mass on a spring, we use a quantum harmonic oscillator. Now, there are many interesting differences between classical and quantum harmonic oscillators, but the one that's really important here is that the quantum oscillator can't have any energy that we want. In fact, the energy can only come in integer multiples of a constant determined by the properties of the oscillator. In essence, the energy of a quantum harmonic oscillator comes in chunks. Every oscillator can have only a whole number of these chunks of energy in it. So let's set up our system in the same way as the classical system. Just take a ring of quantum harmonic oscillators and start increasing the number of them to see what happens. We'll prepare the state so that there's a single chunk of energy in a single oscillator. Now, these oscillators can still interact and pass this chunk of energy between each other. However, due to the nature of quantum mechanics, after we start the system running, we can't exactly say where this chunk of energy is. We can only determine the probability of finding this piece of energy in each particular oscillator. I'll represent this by how red each oscillator is. The more red, the higher the probability of finding the unit of energy in that oscillator. Okay, let's look at how this works. Like in the classical case, when the number of oscillators is small, things look pretty random. Now, like we saw in the classical case, around n equals 500, we see a big change. We get two main regions where the probability is highest, which propagate around the circle. However, after a while, we again see the probability start to smear out over the full ring. As we increase the number of oscillators even more, this high probability region gets even smaller and holds together for longer. When we reach n equals 5,000, we really start to see how we can get particles from this theory. The two very red regions are very small and also quite stable. For the entirety of the simulation, we don't see these regions smear out nearly as much as we did for the case of fewer oscillators. As we might expect, when we take n to infinity, the non-zero probabilities are localized in 2 points which travel at a fixed speed around the ring. As it turns out, the speed is exactly the speed of sound we found in the classical case. So it seems that instead of having sound waves like in the classical case, we have sound particles, called phonons, in the quantum theory. The two parts just come from the fact that there's a 50% chance that the phonon is traveling clockwise and a 50% chance that it is traveling counterclockwise. So why do we consider these actual particles, whereas in the classical theory we did not? Well, remember in the quantum case, we have to have discrete units of energy in specific oscillators. In the case that we only have a single unit of energy in the system, there's no other option than to have it localized at a single site, even though multiple oscillators may have some probability to be the home of this unit of energy. In this sense, each unit of energy behaves very much like we would expect from a particle. They always have the same properties, and they're localized in a specific place. In the classical case, we don't have any restrictions on what the energy in the system should be or how we configure that energy. so we don't have a similar interpretation. Alright, let's recap a bit. We can visualize a field theory as a collection of a bunch of harmonic oscillators really close together. The only difference between the classical field theory and the quantum field theory is how these harmonic oscillators behave. In the quantum case, the energy of each oscillator is quantized, so we can only put energy into the system in set units. When we place a single unit of energy into the system at a specific point, the unit of energy behaves very much like a particle. The possible sites where we could find it are localized points which zoom around the ring at the speed of sound. This is why a theory of quantum fields gives rise to physics involving particles. Now, before I wrap up this video, I want to say that I've put all of the code that I used to create these animations in a GitHub repository, as well as some documents which explain the math behind the code. So if you're interested and want to play around with it a bit, I'll link it in the description for you to check out. While its interpretation as a bunch of quantum harmonic oscillators very close together is very straightforward, quantum field theory remains an incredibly mysterious area of research due to its mathematical complexity. In fact, even one of the 7 $1 million Millennium Prize problems is really a quantum field theory problem. Nevertheless, despite these mathematical difficulties, theory has been arguably the most successful of any physical theory to date, giving us the full standard model of particle physics, as well as finding applications in other fields such as condensed matter physics and nuclear physics. Quantum field theory is an absolutely beautiful theory, both in terms of physics and mathematics, and has completely shifted the way we understand the universe around us.
Towards the end of the 19th century, physics was flourishing. The principles of thermodynamics had helped to kickstart the Industrial Revolution, and Faraday had recently discovered how to generate